Last set of problems. Problem 6A. So first of all, we've got an A matrix. We have x1 and lambda 1, which means ax1 equals lambda 1 x1. And then we have our next set of eigenvectors and eigenvalues, and then our last set, because this is a 3x3, therefore there's 3 eigenvectors and 3 eigenvalues. Some of those might repeat. These ones don't. So A, find the values of Q, R, and S such that A1 or X1, X2, and X3 are eigenvectors of matrix A. Once again, this is what we're going after. Okay, so if I take A times my eigenvector, times each eigenvector, it should be that eigenvalue times my eigenvector, so it should be 0 times x1. So if I go ahead, do this matrix multiplication, column 1, row 1, I should get negative 4q minus 7 plus 3, and that should equal 0. So there's my system. I don't need to do it with these other two rows because it's 0 times every single value, so all of them should be 0. So that means negative 4q minus 4 equals 0, or q equals 1. No, q equals negative 1. For the second one, same thing. Negative 4, negative 5, negative 5, negative 7, 0, negative 7, 3, negative 5, 2. If I multiply it by my second one, it should be negative 9 times x2, because that's the corresponding eigenvalue. So that means if I do my multiplication, once again, it doesn't matter. I'm going to use the second row because it's got a 0 in there. So negative 20 plus 0 minus 5r should equal negative 9 times 5 times this value. That means I have negative 20 minus 5r equals negative 45, or negative 5r equals plus 20. Negative 25, r equals 5. And then my last one, same thing, copied on my A matrix, copied on my last vector for S3, and that should equal 7x3. I can't use my second row this time because zeros in the would make my S go away, so I'll use my last. It doesn't matter which row you use, except I can't use row 2. So negative 20 minus 7s plus 6, and that should equal negative 7, or I guess 7, not negative 7, 7 times 3. So that means negative 20 minus 7s plus 6 equals 21. So plus 20 minus 6. Negative 7s equals 20, 41 minus 6, 35. S equals negative 5. There we go. So that's part 1. B, is the matrix diagonalizable? Yes, it is diagonalizable because lambda 1 is not equal to lambda 2 and is not equal to lambda 3. 3 distinct eigenvalues, which means I have 3 distinct eigenvectors, which means my matrix is diagonalizable because I can write x and I can get an inverse of that x vector. And I know this is what we're going after when it comes to the eigenvectors being diagonalizable. Can we get x inverse? In order to get x inverse, x needs to have 3 independent vectors. 3 independent vectors because our determinant can't be 0, which means these 3 vectors need to be different. They need to be different, which means they need to have 3 different eigenvalues. So it snowballs on itself. So C, using the determinant, state whether the matrix eigenvectors is singular or invertible. So I need to go ahead and put my eigenvectors into a matrix. So Q is negative 1, 1, 1. R is 5, 4, 5, 5, and S is negative 5. I need to find the determinant of this. My determinant should be non-zero. So I'll use the shortcut method. Numbers are small enough. What the heck, is that a 5? What did I write down? Yeah, that's a 5. Looks like an S. S is a terrible variable. 5, 4, negative 5, 3. Okay, so these diagonals, I get negative 15 minus 20 plus 20 minus these diagonals, 25 plus 12 plus 20. Which means those cancel out. I have negative 15 minus 45, 57. Which means it's negative 72. That's not equal to 0, therefore x is invertible. Which is what we knew would happen anyway, because there are 3 unique eigenvectors, because I have 3 unique eigenvalues. Okay, last one. Without calculations, write down the product of A inverse, or x inverse times A times x. Okay, that is lambda. Technically, it depends on what order your x is in, because you can put them in any order, but what happens is our eigenvectors show up, or eigenvalues show up along the diagonal. So I'm just going to go ahead and put them on my diagonal. Lambda 1 is 0, then negative 9 and 7. 0, negative 9, 7. The rest of my elements are 0. There we go. There's lambda. I know I end up with all zeros in a row and a column. Doesn't matter. It's still lambda. There we go. Last problem of the practice set. So here we have 3 vectors and an A matrix. Verify that A, B, and C are eigenvectors of A. Same idea. We should say A equals lambda A. And find the corresponding eigenvalues, lambda 1A, lambda B, lambda C. Okay. Note these are infinite number of solutions. That's how they show up. But it doesn't matter, because I can just pick one of them. Negative 3, 7, negative 5. So I copy down A. And I do my multiplication. 0, negative 1, 1. I can literally just pick one. So I'm going to pick a value of 1 for A. Doesn't matter. It'll still get me what my lambda is going to be. So 0 plus 4 minus 4. 0 minus 11 plus 13. You don't need to do all of the multiplications, but I'm doing it just to verify. Plus 8 minus 10. Especially since, did I copy that first one down wrong? Oh no, it's 0. So that is going to be 0, 2, and negative 2. So here, lambda A is going to be negative 2. The 0, that's where it confused me. The 0 doesn't matter because it's 0. It ends up being 0 because 0 times anything is still 0. Then same thing with my second vector. I'm going to use 1 again. 2, 1, negative 2. When I do this multiplication, I get negative 6, minus 4 plus 8, 14 plus 11 minus 26, 10 minus 8 plus 20, negative 2, negative 1, nope, that should be negative 10, 2. So lambda B should be negative 1. And then my last one, I'll use 1 again. 1, negative 2, 1 equals, I'm only going to do one of these. Negative 3 plus 8 minus 4 equals 1. So lambda C equals 1. Yeah. Okay. So number 1, B is the matrix diagonalizable. Yes, same thing. Lambda A is not equal to lambda B is not equal to lambda C. And then C, assume A, B, and C are all 1. Find the diagonalization of X showing all 4 matrices such that lambda negative da da da. Okay, so I need to find all 4 of these matrices. So first, A is already given to me. Check. X is going to look like this. take my eigenvectors and plug them in as my row or as my columns in X. Okay, if that's the way that looks like, come on, then lambda is going to look like this. These ones go together, these ones go together, these ones go together. Okay, so make sure you match them up. Which means I need to find X inverse. I'll do my row operations for this one. I don't think I've done row operations much in this practice. Okay. Here's to praying things go right. Once again, the solution does it differently, so we'll see what happens. So I'm going to go ahead and swap. I'm going to swap the first two rows. Video cut, because I failed miserably. So I'm going to find the inverse, and I'm going to use row operations, because I haven't done a lot of row operations. I did it once in between where the video cut, and I failed. So I checked my answers in MATLAB, and I am going to do them appropriately this time. So we set it up, 2, 1, -2, 1, -2, 1, set it up next to identity. And then I want to go ahead and do my row operations. So first thing I'm going to do is I'm going to swap rows 1 and 2 because I don't want this 0 here. So that means row 1 becomes this. Row 2 becomes this. And row 3 does not change. Okay, now I want to go ahead and make these 0. So I'm going to say row 3 equals row 3 plus row 1. So that means row 1 doesn't change. Row 2 doesn't change. It's already got the 0 in the spot where I want. And row 3, now I'm adding these two rows. So 0, 0, 1 minus 2 would be -1. -2 minus, or plus 1. Or 1 minus 1, anyway, -1. 0, 1, 1. Checking it, we're good. Now I'm going to go ahead and make these zeros. So I'm going to say row 1 equals 2 times row 1 minus row 2. And then row 2 equals, row 3 equals, row 2's good. 3 equals 2 times row 3 plus row 2. So I'm going to multiply these rows by 2 over on the side here. -2 to -4, 0 to 0. And this one, 0, -2, -2, 0, 2, 2. So now when I add them, I can see them on the side. Or I can subtract them. So row 1 becomes -2 minus 0, which is -2. 2 minus 2, which is 0. -4 minus 1, which is -5. 0 minus 1, which is -1. 2 minus 0, which is 2. 0 minus 0, which is 0. Row 2 does not change. Row 3, now I'm adding row 3 and row 2. So 0 plus 0 is 0. -2 plus 2 is 0. -2 plus 1 is -1. 0 plus 1 is 1. 2 plus 2 is 2. And 2 plus 2 is 2. Checking my work, because I don't want to fail again. And then last thing, I want to go ahead and make these ones zeros. So row 1 is going to be row 1 minus 5 times row 3. And then row 2 is going to be row 2 plus row 3. So I'm going to multiply row 3 by 5 down here. 0, 0, -5, 5, 10, 10. I'm going to go ahead and add in that negative there, so all these numbers change sign. Just trying to make my life a little bit easier, showing my work, a different way to show your work on the side. So row 1 becomes this plus this. So -2, 0, 0. -1 plus -5 is -6. 2 plus -10 is -8. 0 plus -10 is 10. And then I'm adding these two rows. So 0, 2, 0, 2, 2, 2. And then row 3 does not change. 1, 2, 2. So let me double check my work, make sure I've got it all. We're good. Okay, my last step, make these pivots 1 so I get identity. So that means I get 1, 0, 0, 3, 4, 5, 0, 1, 0, 1, 1, 1. It's a nice row. And then 0, 0. And these ones change the sign. 1, -2, or -1. Let's copy things down correctly. -2, -2. Okay. But that's not what I wanted. I wanted my solutions. There we go. This is X inverse. So now I have all of my matrices. So it's X inversed. Times A. Whatever A looked like. So far away. Oh, that's so tiny. -3, 7, -5, -4, 11, -8, -4, 13, -10. You obviously won't have this problem on your exam because you won't be on a tiny screen. -3, 7, -5, -4, 11, -8. -4, 13, -10. Okay, we copy A down. And then we have our X matrix, which is what we started with. 0, -1, 1, 2, 1, -2, 1, -2, 1. And that equals lambda, which we already put together. We found those eigenvalues up here. Okay, keeping in mind the order matters. These need to match, these need to match, these need to match. They go together. Okay, and there we go. I don't actually have to show my multiplication. It just says write, or it just says showing all 4 matrices. When it says find, it doesn't mean you actually need to do the multiplication, but you should know what all 4 of them look like so you can construct them with the information that you are given. Notice neither of these eigenvalue problems did give you the eigenvalue and tell you to find the eigenvector. We also didn't tell you to find the eigenvalues, so you should know all of that information as well. These are just 2 variations on types of eigenvector problems, but there's more variations, so make sure you also use the homework as an example, as a guide, and write down the characteristic equation. A minus lambda I equals 0, forcing the term to be equal 0. And a minus lambda I x equals 0, solving your system in order to find x's. So make sure you can find those from scratch as well. And with that, we are done with the practice problems. So good luck studying.